Section 6.7 is electronegativity and bond polarity. Electronegativity is the ability of an atom in a molecule to attract shared electrons to itself. And you can see this is a, truncated periodic table of the elements with their respective electronegativity values. What you can see from this, cesium has 0.7, fluorine has 4.0. Those are the smallest and biggest electronegativity values respectively. Fluorine has the highest, cesium or francium has the lowest. So the trend is that the value increases going up a group and going to the right. The polarity of a covalent bond, or bond polarity, depends on the difference in electronegativity values of its atoms. So again, electronegativity is how strongly an atom in a bond is pulling electrons to itself. If the pull of electrons is equal, usually when the two atoms are the same element, you're going to have what we call a nonpolar covalent bond. The bonding electrons are therefore shared equally. Imagine like a tug of war where the rope is electrons. If you were to clone yourself and play tug of war against yourself, you couldn't win and you couldn't lose. You would just stay in your place at all times. So that would be a nonpolar covalent bond. The electrons are not going to be spending most of their time around one atom or the other. They're going to be equally shared. But if the electronegativity values are different, that sharing is going to be different. So in this tug of war, you have yourself versus the strongest man on Earth. The strongest man on Earth would be like the most electronegative element. He's going to pull the rope towards himself very easily compared to yourself, unless you happen to be the world's strongest man, which would be pretty awesome, but I highly doubt that any of you are. But this world's strongest man would pull a rope towards him, just like the most electronegative element, fluorine, would always pull electrons in the bonds that it has towards itself. This picture here shows electron density maps of these polar and nonpolar covalent bonded molecules, the first of which is the hydrogen molecule. Since both elements are the same, they have the same electronegativity, so you're going to get an equal sharing of the electrons. And you can see that by seeing how the electron density map here has an even distribution around both of those nuclei. Whereas with HCl, the electrons are not shared equally. They spend most of their time around the chlorine atom. And so if I zoom in here, you can see this little symbol there. That means that the chlorine atom is partially negatively charged. It's not a complete charge. That would, if it was a complete charge, it would make it an ionic compound. It's somewhere in between no charge and a full charge, but not either or. Over here, you have the hydrogen atom being partially positively charged. Because it has fewer electrons than it would actually like, so it's positive. But it's, again, not a complete charge. The electrons are spending most of their time over here, less of their amount of time on the left. All right, so you can use electronegativity values to determine where the polar end of a molecule will be, the partial negative and the partial positive. The electronegativity value of oxygen is 3.5. For carbon, it is 2.5. Nitrogen is 3.0. Oxygen is 3.5. Chlorine is 3.0, fluorine is 4.0. So you can see this is what we call a dipole moment. These species or these bonds are polar because they have a positive and a negative end, and since it has one of each, it's a dipole, and the arrow always faces towards the partial negative, like the electrons are being forced that way. And then they always put this kind of like bar at the end of it. That's kind of like the positive end of that bond. All right, this is another picture that shows electronegativity differences in the types of bonds. If you have an exact equal sharing, this electron cloud is going to be nice and symmetric. If it's an unequal sharing, you're going to have a polar covalent bond, and you get a partial negative and a partial positive. There's still an electron cloud around the partial positive atom, but the cloud is bigger around the partial negative atom. And then for the ionic compound, you have a complete transfer of the electrons. So they've gone all the way over here. You have a much bigger atom there, a much smaller atom there, and those are ions. The table here says predicting bond type from electronegativity differences, which we can do. We have hydrogen, we have bromochloride, hydrogen bromide, hydrogen chloride, sodium chloride, and magnesium oxide. And if we look at the electronegativity values, we have for each hydrogen, they're 2.1, so you get a difference of 0. There, we get nonpolar covalent bonds if the difference is from 0 to 0.4. For hydrogen bromide, we have an electronegativity difference of 0.7, which puts us into the polar covalent range, which they have here for 0.5 to 1.8. Sodium chloride has a difference of 2.1, and 1.9 to 3.3, or anything greater than 1.8 essentially is going to be ionic. And you can look at the rest of those. All right, so in this lecture we have covered covalent bonds, which are sharing of electrons between two bonded atoms. We have dipoles, which are species that have a positive and a negative end to them, or a partial positive and a partial negative end to them. Double bonds are when two pairs of electrons are shared between two bonded atoms. Electronegativity is the relative strength of pull that an atom has when it's in a bond, a covalent bond. Lewis structures are used to represent atoms in molecules, or just the molecules themselves. Molecular compounds are compounds that have only covalent bonds in them. Molecules are the simplest unit of a molecular compound. Nonpolar covalent bonds have an equal sharing of electrons. Polar covalent bonds have an unequal sharing of electrons. Polarity happens when there is an unequal sharing of electrons in a bond. And a triple bond exists when three pairs of electrons are shared between two atoms.